Hi everyone. This week, we're going to start our multi-part, or at least two parts of talking about C constructs like variables and if-then statements and for loops and while loops. And let's start off with the very basics. You can actually, the point of this is that you can create two very similar programs. Now, here's program one and program 2. Now, these do the same thing. The output is the same, but there is a concept, I don't know if you ever heard of it, of refactoring. Now, refactoring involves taking a program and changing it up a little bit, but the output or the result is still the same. So this could be one refactored program in which you have the X and Y presented here as global variables, which means, they are available to everyone that utilizes that is utilizing anything in this program. Okay, in this way, I just call the global var.c. And here we are with local variables in which they're the same program. They still output 3, but the difference is this is where the function is, the main function, literally called main. And you have the x and y that are sitting outside of main. So literally, if you create any other method or function within this program, called the global var, and you reference x and y, it will reference variables outside of the local scope here, thus making them global variables. And I went the wrong way on the PowerPoint. Now with x and y here, they're basically local variables, but the result is the same. We can see the result here after we created local var.c, and then we used GCC to compile the .c. And here we're saying .o, or the output, is going to be called local var. And then now we run local var with the colon / and then local var total equals 3. All right. And here it's the same thing. We do this. The workflow is the same, in which we're creating the source code. We're using GCC to compile the code into what I call global var. And did I already talk about this? I'm sorry. It's the same thing in which we create our source code local var, and then we compile it into local var, and then we're saying total equals 3. I keep on wanting to go the wrong way on my PowerPoint. Now, when it comes to global variable, when it comes to the actual disassembled output, they look very, very similar. As a matter of fact, the start of this, we can see that they look very, very similar. But the devil, of course, is in the details. Now, let's step back for a second, and we see these various register names like RAX and EAX, AX and AH and AL. We see that in the output of our assembly, okay, we see X2, X1, you know, and this is just a small part of the assembly, of the disassembly that results. So you may be wondering, what are these register names? RAX, EAX, AX, AH, and AL. Okay, so it starts out, believe it or not, in the C1103 chip, Intel chip, which started in the early 1970s. It is in fact the first RAM chip. Believe it or not, it wasn't even a CPU in the format that we would know now. Not back then, it was all RAM. Now, one of the first chips that Intel actually came out with, the CPU that we would commonly think of it as today, came out for calculators, believe it or not. And then the first real Intel chip was the C8008-1. And I should probably distinguish these names from their descriptions so they're easier to see. Now, this infrastructure set architecture, or ISA as they call it, was adopted from another company called DataPoint. So DataPoint came up with the architecture, if you will, and Intel basically, quote unquote, adopted it. And actually, a couple gentlemen from DataPoint wound up coming on board to Intel. Now the C8008-1, okay, that was the first real PCU, and I'm going to put this, I'm going to just make this so that it is more distinguished, if you will, but it was the first real chip that Intel developed. It would have been the first CPU to, I guess, to be considered an actual CPU like we would know it. And of course, Intel didn't even create it, they adopted the architecture. Okay, but they also were able to adopt the concept of chip registers. So, chip registers were created in order to temporarily hold data, certain calculations, rudimentary calculations, so that the CPU wouldn't have to use its random access memory, or RAM, because CPU registers, or basically storage, as you can see the way the symbol is developed, it's A, B, C, and D, as in little pools, if you will, of storage. It's infinitely cheaper, quicker, or whatever to use these CPU registers than full RAM. Okay, because it's like you're going outside of the CPU to use it. The purpose of each register has its own purpose. Now, as you progress into time, these purposes get muddled. But we have A, and we call that the accumulator. And what A will do is do things like math equations, like 4 divided by 3 and things like that. The base accesses data memory offset, or as they say, a pointer. So while A is doing math stuff, B is basically pointing at stuff. It's pointing to memory offsets. C is the counter. So you would use the C pool in loops, if you will. And then D is a data register used for overflow, if you will, of math, like multiply and divide results. So that's what D is for. It's for the overflow. Now, if you're wondering when is all this happening, it was released. The 8008 chip by Intel was released in 1972. So in 1972, they were beginning to use these concepts of registers. Now, in 1978, with the release of the 8086 chip, so that's about 6 years, okay, it not only added an additional 8 bits here, so these are all 8 bits. And I should have mentioned that. That's 8. This is 8. And C is 8. D also is 8. All right. Now, the big thing about the next generation, or whatever, the next chip that was released, it added an additional 8 bits, making it 16 bits. So this was your 8. This is another 8. Now, if you wanted to reference the entire thing in a row, it would be, you would just say AX. So AX, you would consider it would have an upper and a lower, a high and a low. That's why there's AH, which is A of high, okay, and AL, which is A of low. So it is possible to isolate and actually reference just the low portion of A of X. You just say, you just refer to AL. Same thing with CX, for example. You could reference just the lower portion of CX by referring to CL and DL. And they did this, of course, for backwards compatibility. Okay? But the release of the 1986, the release of the 8086 chip coincided with not only adding 8 more bits, okay, but they added some new registers. Okay, so we have AX, BX, CX, and DX. And we have these other registers that it shipped with, SI, which is source index. We have DI, which is destination index. We have a bit pointer, and we have the stack pointer. Just so you know, the SP or stack pointer had always been in here, even here, but they never referred to it officially. It was just always there. Okay, and source index indicates where the string starts, and the destination index is where you want to place the string. Okay. Then they released another chip later on in 1985 called the 8386 chip. That, of course, added an additional 16 bits. Okay? And when you did this, if you want to refer to the whole thing combined, they called it EAX, or extended AX, extended BX, extended CX, and extended DX. Okay, now you have AH, AL, AX, and then you have almost like a completely different a replication of it, if you will, and not exactly a replication, but if you will, they added 16 more bits, making a total of 32 bits. So you will frequently, here's the thing, here's why I'm mentioning this. You will frequently I'm going to say in college books, you will frequently see EAX, EBX, ECX, and EDX. Now, the 64-bit version starts with R, so that would be RAX, RBX, and such and such. You're going to see EAX just as frequently or even more frequently as RAX. What does that mean? That actually means that you're like if you're reading a book and it came out not too long ago, you're still going to see references of EAX, even though that's only 32 bits. And that is because the software application that they are demonstrating in these books is still going to be running in 32 bits. So you can fully run a 32-bit application on a 64-bit chip, and there's nothing wrong with it due to backwards compatibility. Generally, software, until only recently, was written in 32-bit because there's a lot of times, unless it's very highly used, there's no reason for it to be written in 64 bits. So that's why you're still going to see assembly syntax and assembly code referencing the registers such as EAX and EBX and ECX, because contemporary software was written in 32-bit. And they did this same for the rest of the registers. So we go from ESI, from SI to ESI, DI, DI to EDI, BP to EBP, and the stack pointer to extended stack pointer, or ESP. Finally, AMD releases its first 64-bit chip, followed by Intel. Okay, that's 2003, and it adds another 32 bits. So now we have, and then we can see it actually adds 43 bits. And now we have, instead of just referring to EAX 1 and 2, we can refer to the whole thing as racks. Okay, and so not only did it add another 32, it adds another 64. And the rest followed suit. So EAX becomes RAX. EBX becomes RBX. ECX becomes RCX. EDX becomes RDX. And then the rest follow suit. RSI, RDI, RBP, and RSB. Okay? And in the case of a dividend divisor, okay, we have the dividend. So in other words, A divided by B equals C. So A is the divisor, or A is the dividend, B is the divisor, and then C is the quotient. Okay, so in this case, A would go here in RAX. B, the divisor, would go into RBX, and the RCX also holds a divisor. Now the remainder, okay, the remainder goes into RDX, the data storage unit. Okay. And then, of course, the quotient, the result itself would go into AX. Okay, in the assembly primer, we have the assembly primer right into the box. So, in other words, we want to move, sorry about this. We want to move into racks, or into AX, the number 3. So in other words, this makes this, we'll just call it AX. Okay? And move into this box, number 4, the value of 4. So RBX 4. So this would be BX. And because you're moving 4 in here. Now, add them together and place the results. Now, can you guess what storage location this would be? That would be, if you guessed AX, you'd be correct. Because you are storing both into RAX, you're storing BX. And as time wore on, there were just more registers added. So we have ABX, BX, CX, DX, DI, SI, BP, RSP. And then we also have these other registers here for the overflow. Let's very quickly re-talk about the compilation process. Okay, so it starts with the source. Okay, and then it goes into something called the preprocessor. And then we go into do the C++ compiler, then assembler. And then we have here the object files. Then we have the linker. And then we have a.out. Now, there's something called pre-processing, in which we include the actual header information. So we're including, this is like the C language's version of their own API. So they are asking you to bring in all the assets in the standard in-out library that they have through the .h header. And here we define macros, in which we format the string right here, and we define the message hello world. Okay, and we're saying printf format string, and that is the format string, and then here's the message. Now here we can show the pre-processing right here, GCC space dash E space dash P, and then this is the name of the program, CompX. Okay, and this is CompX right here. All right. Now let's take a look at the difference between global variables and local variables. Okay, with global variables, we can see that it is a global variable is a global variable. Like I said, it can be accessed by any function within a program. Let's take a look how assembly is affected. Okay, the global variable x is signified by this word dword, and then here is the some place in memory, 40CF60. That is the memory location at OX40CF60. Okay, and notice the x is changed in memory when memory EAX is moved into dword. So we have EAX. Okay, we have this right here. It is moved into dword because we have x equals x plus y. So it's saying that x has moved in to x. This dword has moved into EAX. I should apologize. This value of x has been moved into the register EAX. Okay, and we have x equals x plus y. So the value of EAX is then moved into dword 40CF60. Okay, so what it's saying is that because x itself is a global variable, okay, it's saying that x is changed when EAX is moved into that memory location, because global variables are referenced by memory addresses. Now, local variables are referenced by stack addresses. As it shows, a local variable x is located on the stack at a constant offset relative to EBP. So you see how it says EBP -4, because that -4 signifies it is an offset. Okay, so anytime you see an offset, that is a stack address. And so thus, local variables are in fact referenced by stack addresses. So EBP minus 4 is used consistently throughout this function to reference the local variable x, which tells us EBP minus 4 is a stack-based local variable. And that enables it to be referenced only in the function in which it is defined. Okay, I know this is a short lecture, but it's a little bit to absorb, and I want to give you enough time to absorb it. And next week, we will be working on problems and C constructs that allows us to actually understand how the assembly language is shifted and changed, and in doing so we can actually be better we will be better at looking at disassembled syntax, and that is the key for cracking malware.